Welcome to ICCP 2026. So we are going to have like 3 amazing invited talks right now. So about this section of like typography and trust. So the first speaker, we are going to have like Kristina Molokova from Cornell. She's an assistant professor in the Department of Computer Science at Cornell, where she leads the computational imaging lab at Cornell, and she also works on co-design optics and algorithms to create better, smaller, and more capable cameras and microscopes. Okay, so the talk title will be Trustworthy Computational Imaging with Uncertainty Quantification. Let's welcome.
Thanks so much for having me. Today, I'll show you how to add error bars to inverse problems. So as we've seen from the previous talk, machine learning can really supercharge computational imaging. In my own work, I've shown that machine learning can be really powerful as a prior for lensless cameras. And for extremely noisy clips in starlight, it can serve as a very powerful prior as well to merge very faint signals together to create plausible-looking videos. For photography, this is wonderful. And also, all of these techniques these days are being used in addition in scientific and medical imaging. So in microscopy, machine learning is being used to do deconvolution, to get better resolution, and to inform downstream scientific discoveries. And if you go to the doctor to get an MRI, there's actually a good chance that a machine learning-based algorithm will be used on you. There's actually 1,000 FDA-approved AI algorithms to make MRI faster, sharper, and less noisy. But as we've seen, there are inherent risks. So if you take an undersampled MRI measurement, run it through some standard CNN, UNet, you get back a prediction which looks very plausible. And if you compare it to the ground truth, it looks pretty close. But if you zoom in and squint your eyes a little bit, you can see that the prediction has realistic-looking artifacts that are not present in the sample. We call these hallucinations. And doctors are going to be betting a patient's life that these images are real. So this better be real. Wouldn't it be great if we can still use these very powerful priors, but still have some sense of which features in the prediction are more or less trustworthy? So that's the problem with machine learning, is these days, a lot of machine learning algorithms will give us a point prediction. It'll give us the best guess at what the image should be given some noisy, underdetermined measurements. But really, in science, we need more than point predictions. We need error bars. Carl Sagan said, every time a scientific paper presents a bit of data, it's accompanied by error bars, a quiet but insistent reminder that no knowledge is complete or perfect. And for scientific computational imaging, we need error bars like this. Luckily, over the last few years, there's been a lot of work in conformal prediction to bring trustworthy error bars to these predictions. I'm going to first summarize some of this work and then show you what my group has been doing in this area. So there's a 3-step procedure into getting trustworthy uncertainty bars at test time. The first step is you need some way to predict some notion of uncertainty. And there are several ways of doing this. First, there's sampling methods. For example, you can feed a single measurement into a network that has different amounts of dropout to create several different predictions, which will all be a little bit different. From that, you can build up a mean and variance image. Alternatively, you can do something like an ensemble. So you have multiple different networks, which each will produce a slightly different prediction to build up this mean and variance as well. You can think of diffusion-based models as one of these two. You can query it multiple times to get multiple predictions. However, all of these methods are computationally intensive because you have to run an image through the network multiple times. Alternatively, there's also direct methods to doing this, where you can have a single network try to predict a lower and upper bound. The way this is accomplished generally is that during training one of these networks, rather than having it predict a single image, it predicts 3. One will be a lower bound, one will be the upper bound. And you can do this through an asymmetric loss, which will encourage the model to predict an underestimate or an overestimate. So then at test time, given a new unseen measurement, it'll predict automatically some lower and upper bound. These methods are really fast, requiring only a single forward pass, so we're going to focus on those during this talk. Okay, so given some method of uncertainty, either through sampling or direct methods, the next step is the question, how do we even trust that these error bars mean anything at all? And that's where calibration comes in. So during calibration, what happens is there's a small data set of calibration images that are not seen during training, and you'll feed in your measurements through your reconstruction, get out your upper and lower bound, and form this uncertainty interval. Here we're visualizing this interval in this plot on the right, where you can see this is a line in this image. Whenever you compare to the ground truth, which is labeled as those black dots, you can see how many of those points from the ground truth actually lie within those bounds. This will give us a notion of coverage or miscoverage, so the fraction of pixels that are not within those bounds. And so the goal here is to say, let's actually change these bounds. Let's make them a little bit bigger, a little bit smaller, until we have the appropriate coverage. Say we want to have 90% of all the ground truth lie within those bounds. So you can scale these bounds a little bit until you achieve coverage. And then during test time, with a high probability, you will have coverage on new unseen data. Now, there's a trade-off here. You could have an arbitrarily large interval and have full coverage, right? But then this wouldn't be very informative for the uncertainty. So really, the goal here is, given a fixed coverage, say 95% or so, we want to have the tightest possible uncertainty intervals such that we still reach coverage on the calibration data set. Once we find those scaled intervals to reach coverage, at test time, you have a high probability that any unseen data is going to lie within those bounds with some good certainty. Okay, so all of these methods, they work off the shelf. All you have to do is have some notion of error, calibrate those, and then use those. However, most of these methods were designed for tasks like classification, where you want to calibrate only a few variables. Images are very high dimensional, and so because of this, some of these methods don't work so well for these problems and result in much larger bounds than we would like. So my student Cassandra has been working on this front of trying to improve these methods to have much smaller uncertainty intervals. And also, once we have uncertainty, what do we do with it? So let me go through the first project. So to remind you, there's this important calibration step in these methods where you have to calibrate those bounds until you achieve the desired risk. In previous methods, would simply scale those bounds with a constant scaling factor. That means on this graph right there, you can scale these lines up or down, but you cannot change their shape. So this leads in a spatially invariant scaling that's not dependent on any of the local features in the image. So we came up with a new method called cutesy, where we will change the calibration. Rather than calibrating something after the prediction, we calibrate the input to the network, which means that the calibration can globally affect the whole image. So now we can actually change the shape of those lines. And so this leads to a spatially adaptive scaling. So if you compare the bounds before and after calibration, it's actually sensitive to local features within the image. So at test time, what this looks like is previous methods would predict all at once a lower and upper bound, but our method now is going to require multiple queries to this because our network will predict a single image that's conditioned on a quantile between 0 and 1. So if you change the quantile q here, you can see that the prediction is going to change as well. So at test time, what happens is we query the network at q equals 0.5 to get the median prediction. And then to get the upper bound, we'll choose a higher quantile that's set through the calibration procedure to achieve coverage, and a lower quantile to get our lower bound. If we subtract these two quantities, we get a notion of the pixel-wise uncertainty in the scene. So in our paper, we compare this on several different inverse problems, including MRI, denoising, and quantitative phase imaging, and we show that our method will enable smaller interval sizes than previous methods. It's also much faster than deep ensembles. Excitingly, we found that if we take a look at one of our predictions, and here you can see that there's actually a hallucination present. There's this feature that's not present in the ground truth. And if we look at our predicted uncertainty, it actually marks this region as red, as a high uncertainty region. And if we compare to the true error, it correlates very well. So this gives us confidence that our uncertainty maps are doing the right thing and can actually help us detect places where there could be hallucinations in the reconstruction. The other exciting thing is now we actually have a way to predict any quantile. So we could actually query the network with multiple different quantiles and build up the entire quantile function of the prediction. This is related to the conditional distribution. So with a little bit of math, we can actually predict P of x given y from this network and get some notion of the distribution at each pixel in our reconstruction. We've tried this for Gaussian and Poisson denoising, and given noisy measurements, we can plot the pixel-wise predicted distributions at different points in the scene. And as we increase the amount of noise, these predictions become wider, showing that there's more uncertainty and more variance in the measurements. Okay, so this project essentially presents a way to do spatially adaptive conformal calibration, which results in smaller intervals, and also a way to predict the conditional distribution, which previous methods could not do. So now that we have uncertainty, what do we do with it? Well, we could give this to a doctor, and they could say, okay, maybe I shouldn't trust those regions. But more actively, we can actually use it in the loop, potentially, to acquire better measurements. So one application here is in scanning microscopy, such as confocal, two-photon, and multiphoton. Generally, the microscope system will actually scan point by point to build up a whole image or volume, which takes a lot of time. So there's a trade-off here. You could have a very high-power laser and a very long dwell time. So essentially, you're averaging a lot of signal together to get really good image quality. But this results in sample damage due to this high-power pulsed laser, and it's also very slow. Alternatively, you could scan it really quickly and get something that's very noisy, but this is going to be very, very fast. We think of this as kind of a denoising problem of, can we really break this trade-off and say we want to do this really, really fast, but still get, as good of image quality as possible. Moreover, we say, okay, let's actually try to use uncertainty in this setting to show us how we should resample the sample. Okay, so this is our idea. We want to use uncertainty in the loop for adaptive acquisition in microscopy. So we have a scanning microscope. We take one very quick, noisy scan. Then we're going to run this through our denoiser, which will also predict the uncertainty at each pixel. We simply threshold the uncertainty, and we use that to tell the microscope where we want to rescan. We acquire new measurements, which allows us to do multi-image denoising to get a better estimate of the denoised image. Okay, so we scan, predict the uncertainty, threshold, rescan, and do this in the loop. In our synthetic results on different samples, we can see how these uncertainty adaptive masks change over time. And as the uncertainty decreases, we'll be scanning less and less of the pixels in the image. So this is also very sample dependent. So if you have like a very dense, complicated scene, you probably need to rescan most of it. But if you have a pretty sparse scene, you can save a lot of time. Here's an example where we have a noisy measurement and then our denoised image and the uncertainty. And as we have more measurements, the uncertainty decreases and we get a better prediction. Here we're going to zoom in to one region where In the first denoise result, there's actually an artifact. So there's this little loop that appears. And in our uncertainty, this is labeled as a high uncertainty region, and the loop is not present in the ground truth. However, as we add more measurements, this loop will actually disappear. And so we're actually able to mitigate hallucinations by adding more measurements. And we can do this adaptively. We don't have to rescan the whole thing. We can only rescan the most uncertain regions of the image. In this case, this results in about only scanning 36% of the pixels and about 2.7x less light dose to the sample. OK, so I've showed you now these two projects. One is to try to make the spatially adaptive calibration procedure. Another is how to actually use the uncertainty maps in a useful way for microscopy, which can make it much faster and have less light dose to the samples. Some of the open questions and limitations are all of these methods provide only marginal coverage, and they require a good calibration data set. So if you calibrate on apples and test on oranges, it's not going to work anymore. We also do all of the adaptive work only in simulation, and we don't have hardware results yet. Some open questions are how to incorporate these sorts of methods into physics-informed reconstructions, and also for diffusion-based methods, which are right now very, very slow for this, and also how to do this for moving and dynamic samples. I would like to thank my lab and my postdoc lab where we did the adaptive work, and you can add error bars to your methods as well. Happy to take any questions.
Thank you. We have limited time for 1 or 2 questions. Any questions from the audience?
Thank you for the talk. I like the slide on hallucination detection using the uncertainty maps. Have you seen examples of the opposite where the model's really confident, but it's a hallucination? In some sense, hallucinations could come from bias, low variance, but high bias and stuff like that.
Yeah, I think those are really hard to find. The procedure I showed you here will still work if you have a good calibration data set, but it'll give you error bars that they're very high, essentially.
I see. Thank you.
Beautiful work. Question about the speed of the training with this conditioning on the quantile there. Is it fast enough to be compatible with sort of live on-the-fly reconstructions? Like how long does it take?
So you would train it beforehand, and at test time it's very fast because you only need 3 forward passes.
OK, sounds good. Due to the OK, one last question over there. Quick question.
Sorry, I had a quick question. You had mentioned that there's like sampling methods and direct methods. I also agree that like direct methods are really nice because you have much less of that like iterative runtime kind of constraint. Is there any or can you offer any intuition or observations on like the quality of sampling versus direct methods in general? Like, do you observe any penalty in terms of the quality of the uncertainty reconstructions that you get?
Yeah, I think the ensemble methods do a little bit better for the diversity, and so they are the state of the art generally. In our work, we show that if you don't have so many ensembles, if you only have 10 or so, our method is comparable to that. But of course, if you have like hundreds of ensembles, it'll probably do better.
OK, great. We can always continue discussion during the coffee break. Let's thank the speaker again. Thank you so much. OK, so the second speaker, we have Pingshen Huang from UIUC. She's a professor and retro faculty scholar in the Department of Materials Science and Engineering, and also the associate director of the Materials Research Lab at UIUC. Her research is focused on transmission electron microscopy and ptychography of two-dimensional and electronic materials. So the talk title is Building the Future of Atom-by-Atom Materials Characterization with Electron Ptychography. Let's welcome.
Okay, hi everyone. everyone. I'm so excited to be here, in part because I'm one of, I think, 2 electron microscopists here. And so I'll give you a little bit of background into what we're doing here and why I think we're really at a revolutionary time in electron microscopy. And we have so much to learn from computational imagers like yourselves. And I hope you will all flock to our field and help us solve our many, many problems. OK. So the tool that we use is called a scanning transmission electron microscope, or a STEM. So we take these electrons, we shoot them out of an electron gun at the top. They go pew, pew. And then we accelerate them so they're going very fast, about half the speed of light or even more. The reason we do that is then the electron wavelength is about 2.5 picometers. And so that allows us to look at very, very tiny things like atoms. That's what I spend my day doing, photographing atoms, but not photographing, but electrographing. So we take that, we use lenses to focus the beam down to a really small spot, about an angstrom, about the spacing between atoms. And then we scan the electron beam back and forth on the sample. And historically, what we used to do was we would have a detector that counts electron count. So we'd have an integrating detector, we would call it like the annular dark field detector, and we just count the electrons that hit that detector as I move my beam around. And as you can see on the right, we can see single atoms this way. This is an atomic layer of moly disulfide. So you're really seeing individual molybdenum atoms or 2 sulfur atoms. And we work very hard to make images like this, and I think Richard Feynman put it best into why we do what we do. Is he says what you should really do is make the electron microscope 100 times better. Now at the time they only had 10 angstrom resolution, but the motivation is still the one that we work on today. He says it would be very easy to make an analysis of any complicated chemical substance. All one would have to do is look at it and see where all the atoms are. And that's what we do. We cut up a computer chip, we put it in the microscope, we see where the atoms are. We take the coronavirus, we put it in the microscope, we see where the atoms are. That's what we try to do. And the thing that we're fighting is the fact that electron lenses are very bad. So we have aberrations. They are unfixable for electron optics because of Maxwell's equations. So that's fun. And really, the quality of lens that we're working with, a typical round lens, has aberrations that look like this. They're spherical aberrations. They're like looking through the bottom of a Coke bottle. And so in the last 100 years since electron microscopes were invented, we have been fighting the bad optics of electron microscopes. And we've mostly been doing it in one way, which is called aberration correction. It's a hardware-based approach. Basically, you have a lens, it is bad. It has aberrations. So to correct it, you put other bad lenses on top of it, and you hope those lenses are bad with the opposite sign. And then they introduce other aberrations, and then you stack more lenses on top of those with different aberrations, and then you use a set of computers or one computer to measure the aberrations dynamically in your sample or in your microscope and correct them several times during the day. This is the process that has led to several Nobel Prize winning discoveries, including for the invention of the electron microscope and cryo-electron microscopy. Because it is a foundation of scientific discovery, even though it sounds like the worst possible way to do things. And there have been consequences of the way this works. So you can buy a microscope without this fancy aberration correction. It will cost you some money, but it will be maybe a couple $1 million. You can buy the fanciest microscope that can give you the best resolution possible. That one's on the left. If you go and get a quote these days, I hope your heart doesn't stop because it might run you $8 million. So that's not great. But the reason that we do it is because if you look at a sample without the aberration correction, that's the image on the bottom, you may get something like 1.5 angstrom resolution. So you can see atoms, but they look a little blurry. And with the aberration corrector, you get under an angstrom, sometimes as low as 0.8 angstroms, 0.7 angstroms. And we care about that a lot in science because 1 angstrom is this lower limit of spacings between atoms. So you can get exceptional detail, really look within a material and see where everything is. So what we're doing right now is we're going through kind of an awkward teenage phase where at least some of us, the smarter ones of us, are discarding this old paradigm, this one that has guided us for the last 100 years, of trying to correct those aberrations with hardware and starting to do electron ptychography. So the setup over on the left is the same as before. We still have the electron gun. It's still shooting the same electrons through the same sample. But instead of a counting detector at the back, we put a camera, a pixelated detector. And so we're collecting the electron, not images of the sample at all, but images of the scattering pattern that comes out of the sample on the other side as we scan the beam around. And so this has been enabled by a hardware advance. We now have better detectors that can run fast and collect these images with high dynamic range. And then we feed them through algorithms, and the algorithms have gotten a lot better too. And basically what these things do is they guess an initial electron beam, we call that the probe, and an object. And then it does a forward process. It scatters the beam through the test object, calculates the exit wave, calculates the diffraction pattern, and then compares them to the experimental diffraction patterns that we have. Using that comparison, it updates its guess of the object and probe and iterates the process over again. Usually we run this several hundred to several thousand times, and usually using the most common codes, this can take anywhere from 30 minutes to several hours to overnight. Okay, so why would you do this? Well, let me show you. So on the left is an image acquired with the standard imaging mode of the microscope, the old school method of doing it. And on the right is my ptychography, and I'll just update my guesses like the algorithm would. So we initialize with random noise. And we'll just go through iterations 1 through 15 to see how the image progresses. So at 1, you already see the structure, and as we continue to iterate, it gets sharper and sharper until you can see all these atomic features that weren't present in the other style of imaging. And again, I'm stopping after iteration 15. We usually run for about 2,000. And so after this process, our images are very, very good. Electron ptychography is now the highest resolution imaging method of any microscopy. Am I allowed to say that? I think so. So in this plot of feature size versus year, you can see there have really been only, until now, 3 great revolutions where we have dramatically increased the resolving power of microscopes. Starting with the invention of compound-like microscopes all the way on the left, going to electron microscopes benefiting from their smaller wavelength, correcting their aberrations. And then here we are in electron ptychography, and you can see the era of aberration correction is starting to stagnate, and the electron ptychography era is just on its hockey stick upwards. So this is really exciting, and people are starting to report breathtaking resolutions. Let me show you some work from my own group. So on the top, we have our aberration-corrected microscopes, the best conventional imaging mode money can buy. You can get just under an angstrom with that microscope. But once you do ptychography on the microscope, now we have 0.4 angstrom resolution. And what's really important to me equally as that doubling of resolution on the top end is what happens on the bottom end microscopes, those without hardware-based aberration correctors. These were the ones where we were getting about 1.7 angstrom spatial resolution using the conventional hardware. And then with ptychography, we hit 0.4 angstroms, again, just as good as the best aberration-corrected microscopes out there. And this is really important because not everyone has $8 million in their dresser drawer to go and buy that best microscope in the world. But using ptychography, you can make a medium range, much more affordable and accessible microscope perform like a great one. You can do other things, like just see how good of resolution you can get. So I had a postdoc who was just amazing. We were asking the question, like, how well can we see an atom, right? And so we took a material that's just a couple atoms thick. It's this twisted bilayer tungsten diselenide. You don't really need to know that. But on the left, we're starting to see little bumps that are less than 15 picometers apart from each other. This is actually getting pretty close to Feynman's dream of making the microscope 100 times better. And when you do that, not only do you see the atomic structure, as he predicted, but you see even more than that. For example, this little thing in the red box is a single tungsten atom. Here it is in color. And oh, you guys are all imaging people. So I can ask you, does that look round? No, it's not. Actually, what you're seeing is a type of thermal vibration. The atom, this is at room temperature, vibrates due to heat. It's vibrating not isotropically, but anisotropically, like this. And you can see it with your eye, because we push the spatial resolution so far. So that amplitude of vibration is like 5 picometers, 5.6 picometers in one direction. And that is enough to blur our image correspondingly. So it turns out if you look at this lane scale, everything you see is new. And so we stuck in the first sample we could think of to study, and we imaged this thermal vibration, which turned out to be one that had been predicted but never seen, called a Moiré phazon. And then that might be important for like superconductivity, so that was fun. And then Physics World turned around and told us we were a top 10 breakthrough in physics last year. Another thing we're doing is going beyond 2D to 3D, so you'll hear probably more of this from Colin, but one of the exciting things about ptychography is that you can do it both in 2 dimensions, or you can solve a 3-dimensional representation of your object. And this is pretty different from how we historically have gotten 3-dimensional information at the atomic scale, which we would do by electron tomography. So like an MRI, you'd take an image of your sample, rotate the sample, take an image again, and reconstruct in 3D from multiple tilts. With multi-slice ptychography, you can do this reconstruction by just solving the object in 3 dimensions. So this is our sample. It's made out of 2 distinct layers. Actually, it's the same image that I showed you before, but now we're looking at it with the depth slices on the right. And you can see maybe that it's made of 2 different layers that I can see individually as I slice through different slices of our sample. So we see first 1 layer of atoms, and then another hexagonal layer of atoms slightly rotated. And for very thin samples like this, it turns out that taking that information and then augmenting it with a couple of priors, namely that atoms are discrete objects that are spaced an average of whatever the spacing of this material is away from one another, you can recover in 3 dimensions the entire atomic structure of this system with something like 5 picometer precision in all 3 dimensions. What else can we do with ptychography? Well, like I said at the beginning of the talk, there's a lot of power to this new method, but there are also a lot of downsides. We're trying to do science here after all, and we're trying to discover new and unknown phenomena. And so things like direct interpretability and quantitative accuracy of our methods is extraordinarily important. These are things that we have always had as electron microscopists, but now in the world of electron ptychography, we don't have or are not sure whether we have. And there are other problems like the speed it takes to acquire data and the fact that we don't get instant feedback when you use these iterative methods. I told you we're often running reconstructions for hours or more. And so we're also working on ease of use problems. I like to say that the difference between electron ptychography and hardware-based imaging is between like a cell phone with a digital camera and film. Like we have, by advancing our science, gone back to the film days in that we have to go back and reconstruct our data much as one would process film. So there are many people in the field working on this problem. But one that has come up over and over is this trade-off between speed and resolution. And what I'd really like to do on the microscope is know what I'm looking at while I'm looking at it. And so my student Rahim and his collaborator Kieran have been working on this convolutional neural network approach to really do this thing live. So the standard method with an iterative method, so this is examples with the TIRAD code on the bottom, reconstructing a bunch of different atomic structures. We've pulled it before it converged, just to get a 30-minute understanding of what the image looks like. The top is our neural network. We call it Tyrannosaur. It takes 5 seconds to do this. And it's just as good and strangely sometimes better. So if you want to hear more about that, you can see Rahim's poster today. And the key is that our acquisitions are fast. They're 30 seconds apiece. And so a 5 or 25-second reconstruction finally allows us to do this thing that we love to do, electron ptychography live. So yeah, so that's what we're working on. We're pushing the resolution both in 2 dimensions and 3 dimensions so that we can see everything from thermal vibrations of single atoms to the 3D atomic structure of materials. We're making microscopes cheaper and more accessible by trying to see how we can move away from hardware-based aberration correction. And then trying to make this method, which I really believe is the future of electron microscopy, faster and easier to use. So with that, here are some of the papers that I have mentioned and the wonderful people, collaborators, and students who actually did this work. So thank you again.
Great, thank you.
Yeah, question. In optical microscopy, and indeed in photography, correcting aberrations is a tricky technology because of noise. It tends to enhance noise. Is there a comparable problem in the kind of reconstruction or aberration correction that you're doing?
Oh, it tends to enhance noise. It does enhance noise, but not terribly so. And in the systems I've been studying so far, we choose them because we can dump electrons into them, right? So, actually, our methods are still, ptychography is generally more dose efficient than like counting detector methods, just because we're using more of the electrons that we used to throw away. But absolutely, that's something that we worry about all the time, is how can we do this without worrying about noise and amplifying noise?
So you mentioned cryo-EM and you mentioned imaging, for example, the coronavirus. How far away are you from that kind of imaging with electron ptychography? Because you mostly showed crystalline samples.
Right. Me personally, very far. I think the field is also somewhat far. And Colin is working on this and may answer your question during his talk. But right now, the algorithms operate rather poorly at very low dose, very low signal to noise. And then at least the modes that I've been showing you, right, regular ptychography, you're acquiring many times from the same region. And that's true for Fourier ptychography as well. And for a biological sample, that sample will be changing as a function of time. So that's a pretty significant problem that you have to deal with, given our models assume an unchanging object.
Okay, thank you so much. Let's continue discussion during the coffee break. Thank you so much. Okay, so. Great. So Okay, so we have the last speaker for this session from Colin Opus. He's an associate professor at Stanford University, alumni, and also from SLAC. His research focuses on explanatory methods, reconstruction algorithms, and software codes for simulation, analysis, and instrument design of scanning transmission electron microscopy. So the talk is about electron tomography and ptychography with end-to-end parameter refinement and deep learning regularization. Let's welcome the speaker.
Perfect. All right, thank you guys so much. I really want to thank ICCP for inviting me to give this talk. I want to echo what Pinchane said. We are very grateful to the community of folks in this room because as you're going to see in this talk, we are using many, many, many of your tools to improve our own reconstructions and our own scientific experiments. So I hope you like repetition, right? Learning is repetition because I'm going to show essentially the same pipeline as Pinchane showed because we use the same tools, the same algorithms, the same methods. Really the only difference I would say is I don't like 2D materials and I don't like looking at them, but I did include one of Pinchane's reconstructions in my slides here. So again, just to show the sort of history of electron microscopy, right? We use the electron microscope because it has unmatched spatial resolution. The wavelength can be made arbitrarily small, in this case picometers, and this is sort of a history of the same material, silicon nitride, different generations of electron microscopy measurements. And you can see after the resolution revolution of aberration correction, shown on the upper right, the ground truth of the specimen is finally revealed, right? Instead of 6 blurry blobs, you actually have 12 blobs as you go around the circle, and those are your individual silicon and nitrogen atoms there. So here's a picture of what these different generations of electron microscopes look like, because many folks in this room have not seen our gigantic sort of columns. But the scope initially actually started out about 2.5 stories tall, then it shrank down a little bit, and now it's getting taller again as we add more optical elements. And I also want to very quickly mention, too, that upper left image was taken on film, the middle image on a CCD, and then the right image on these direct electron detectors that I'll show here. So I'm just barely old enough that my first electron microscopy was done on film exposure. So how do we actually achieve this resolution below 0.5 angstroms? And in this case, to echo what Christina pointed out, the importance of having error bars here, this has about a 1 picometer error bar in the positions of the atomic columns here. So the first one that Pinchane mentioned is aberration correction, right? We put additional optical elements that correct the bad aberrations of our round electron lenses. The second one that was especially important for biology here is direct electron detectors. These are essentially CMOS chips that are open to free space. Electrons go directly into the chip, cause some distribution of holes in electrons. We collect them, and we can sharpen our image. This is a comparison of a biological sample with a CCD versus the direct electron detector. But the third method that I really want to highlight for this conference is computational imaging. So the raw data is what I'm showing this movie on the lower left here. The upper right is the reconstructed image, right? This was done some time ago, so it used a pretty simple Gerberg-Saxton phasing algorithm here. But without the computational imaging tools, and then these algorithms to reduce and refine the sort of remaining 5% aberrations that are left over after the hardware aberration correction, you wouldn't be able to get such a sharp image here. And then, of course, for us, sample preparation, right? If you're not looking at a 2D material, you have to make sure it's thin enough that the electrons can go through it here. So Pinchane already mentioned this, but traditionally we used to scan across the sample and collect a single monolithic pixel integrating all the electrons scattered out to it. And this, I'm going to show some examples using tomography in this imaging mode here. But these days, because we have access to these direct electron detectors, we can make a full measurement of the forward scattered electron beam at every probe position here. So that's where the name 40STEM comes from. We have a 2-dimensional grid of probe positions and a 2-dimensional image at each probe position. And so ptychography, of course, relies on this scanning transmission electron microscopy measurement here with a full image of the electron probe. So a brief note on phase contrast here. This is a 2D material, and I really like highlighting it to show the sensitivity of phase contrast. So resolution is important, precision is important, but also sensitivity. The phase shift is so small, and yet the electron phase shift is strong enough that we can measure the phase shift of one carbon atom here. So every white dot is just a single carbon atom. And this was a study on grain boundaries in graphene. The details don't really matter for this talk. So ptychography, of course, we scan over the sample surface, often with some defocus, and then we use the redundant information in overlapping probes, and we can use this plus some forward physics to reconstruct the sample. So just showing pretty much the exact same thing that Pin-Chain showed, a guess for the initial probe, the empty object that we start with. We calculate the forward scattering at each of those red dots. That's the probe positions. We compare that to the experiment, measure the difference, and then simply back propagate using the adjoint operator. And within about 5 or 6 iterations here, you can see we converge on this much, much sharper image. And the probe itself has become aberrated because we're solving and fully deconvolving for those aberrations. So this is a quick comparison of different methods showing a gold nanoparticle on amorphous carbon. The upper left image, the dark field, that's that single monolithic pixel. It's out of focus because we defocus the images to do ptychography. And then going left to right are just different algorithms that are more computationally intensive but produce better and better images, ending with ptychography there. So I want to just quickly show what we've built on the microscope. As Pin-Chain mentioned, getting live feedback is incredibly important. So we are now at the point where my group's built a little software stack that sits on the microscope, allows you to browse all your data, your gigantic 4-dimensional data sets, but more importantly, see live reconstructions. So it actually, for us, a full scan is about 3 seconds, give or take, because we operate at 120,000 images per second. So that's about 6 terabytes of data every minute or so here. The data sets are streamed directly to my group's little pocket cluster with about 4 GPUs on it, and then we do reconstructions in 10 milliseconds. So the 10 milliseconds are done with an algorithm called single sideband, and then for the iterative ptychography that I'll show you in a moment here, it ranges from about 10 seconds to, as Pin-Chain mentioned, 10 hours, right? So a huge range, but we're also working on speeding it up here. So the machine learning part of this talk, I want to highlight 2 sort of loops that different groups are using. So this is the first that TIRAD, for example, uses. This is just taking the inverse problem of ptychography and then applying auto differentiation to solve it, right? So all we need is the physics model that converts from our representation of the object and our microscope parameters, pass them into the physics model. You can predict the intensity distributions. Your loss is the difference between those, and you back propagate and update. And so, for example, the MIT ptychography code Phaser or the Cornell code TIRAD, they use essentially this loop. So what my group and several others are working on now is adding generative machine learning to this loop. So I'll show 3 different advantages of using this architecture. We do not directly learn the object anymore. Instead, we backpropagate from our loss function and update weights in a deep prior, a deep image prior, or an implicit representation, which then generates the object. And we also auto-differentiate on the microscope parameters, because we still need to solve jitter in the probe position, aberrations, lots of other little pieces here. And then everything passes through the physics model. So a quick note on hallucination here. We don't worry about that as much, because we compare using both error and, of course, cross-validation, where we leave some data out, the results of using the deep prior or not using the deep prior, but everything must go through the forward physics model. So if the reconstruction is not a better representation of the measured data, especially in the cross-validation leaves some of it out for validation sense, it's not a better reconstruction here. So for ptychography, we started with off-the-shelf algorithms, in this case using a UNet as our deep prior on the input to the object and the input to the probe. We downloaded the GitHub repo, plugged it in, ran it, total failure. It did not work off the shelf. So my hypothesis for this is that this is the difference between our sort of physics-based measurements versus natural light incoherent sort of imaging with multiple color channels. So I think that the signals are way, way too correlated for this to sort of work off the shelf. So we modify it very slightly. We run the traditional gradient descent algorithm for about 10 to 100 iterations, and we use that as our input, in this case into the UNet, and then learn the weights of the UNet to sort of fine-tune the reconstruction. So we just do the traditional reconstruction for a couple loops in sort of an autoencoder sense, and then instead of random noise being passed into the network like you might see in white light imaging or multicolor imaging, and then we update the weights to sort of fine-tune it there. So why do you want to do this? Well, here's the first reason, speed, right? If you do stochastic gradient descent, it can take thousands of iterations to converge. In this data set, my postdoc deliberately spaced out the probes really, really far. We have very little redundant overlapping information, and that causes slow convergence here, especially of the thickness signals, the low spatial frequencies. But if you just put it into PyTorch and use the atom optimizer, you get a massive speed boost. So it's much better than first-order methods here. You can see in about 500 iterations, we're already seeing the gold nanoparticles on the carbon support. But if you switch to the deep image prior as the input, it's much faster. You get a better reconstruction after 50 pre-training and 10 deep image prior reconstruction iterations than you do after 500 iterations using gradient descent or pixelated atom in this case. Now, I should mention the deep prior loop takes longer per iteration, but we're still winning by more than a factor of 10 here. And so this is actually kind of an old result at this point. We're now at the scale where we're doing the full reconstruction loop in about 5 to 10 seconds, give or take here, and hoping to get that even faster, as I'll show. So here's some data set from Cornell. Very, very, very low signal to noise. Every probe measurement in the upper right there is essentially just a couple electrons, a few dozen electrons on the sensor. And this is because this is a metal organic framework, extremely beam sensitive, right? And so the upper middle panel is the reconstruction and its Fourier transform using the pixelated model in our code. The upper left is with the deep generative prior. And we've compared it using the deep prior on the probe or just the image or on both in the upper left. Doing it on both is definitely the winner in terms of quality. So I just want to loop through all the different structural units here to point out the incredible amount of detail you can see. In these linkers, metal organic frameworks are mostly empty space. That middle dot in the middle is essentially 2 zinc atoms stacked along a column and single zinc atoms, that's those 4 red dots, with benzene-like rings linking them together in the diagonals. And you can occasionally see in many of these frames sort of the benzene shape, this hexagonal expansion of those carbon rings, right? And that's from data that looks like the upper right here. OK, so looking at Pinshane's data here, excellent, excellent data quality. And this is a really good test of the theoretical resolution along the beam, right? Because in ptychography, if you do the calculation for electron ptychography, you'll see we can get half an angstrom in plane pretty easily. If we image outside of the numerical aperture, right, often you can get down to about 0.2, even 0.17 angstroms. That's what the Cornell groups have shown here. But along the beam direction, it's much worse resolution because it's very ill-conditioned. Optics folks are used to numerical apertures that are actually reasonably large. In the electron microscope, we're talking about milliradians, right? Very, very, very close to parallel illumination. And so in the upper right, the slice along the beam there, you can see if you do a pixelated reconstruction, you can, the third row down, panel E, you separate the top and bottom layer. But this is another reason why we really like these deep priors. Without any additional tuning, they recover almost the ideal 1 nanometer or 10 angstrom resolution along the beam. And if you apply a little bit of positivity and softmax regularization, you get nice sharp atoms. And we're fitting it and hitting about that 10 angstrom or 1 nanometer theoretical limit here. So able to separate out the 2 layers of that twisted bilayer. And so I think one of the previous questions asked was about biology. We're also applying this to biological systems. But I want to be clear, not very well. So this paper with my group and Henning Stallberg's group is where this data came from, published a couple years ago now, and Newt Muller-Kaspari. We were able to get about 5.8 angstrom resolution using electron ptychography, but that's nowhere near the sub-2 angstrom electron reconstructions that have been done with plane wave imaging here. So in this case, for example, this is the Phi92 bacteriophage. It was somewhere around 8 angstrom resolution, as I recall. So we're still not approaching what the cryo-EM community is doing. But that being said, they've also been working on their tools for 20, 30, 40 years. We did this project in about a year. But I do not actually think that we're going to beat the plane wave imaging of cryo-EM, especially given new deep learning codes available like CryoDragon for those reconstructions. But nevertheless, this is a great platform to also test. For example, when you use a deep prior, what architecture you should use. Here, there's a little bit of a trade-off. As we add more layers, the reconstruction gets faster and faster and faster, but it can become more unstable. And I don't have time to go into the details, but there's slight artifacts there. OK, so I have online tutorials. If you want to check out our Tycho code, here is an example link you could follow. I want to take a quick digression. Let's see if this works, just to show something that I think all groups should think about if they're doing computational imaging, how you actually share your reconstructions here. So this is what comes out of our reconstruction code. Essentially, this is using the AnyWidget framework, JavaScript, and Python. You can just export into HTML and very quickly make nice browsers to be able to see the sort of different atomic scale details, change the color map, change the contrast, whatever you want. And so this is a gate-all-around FET transistor. You can see the silicon sort of surrounding the gate. And if you zoom in, poly-Si, hafnium, high-K dielectric, TIN, lots of different sort of structures there. So I just wanted to make a quick call out and plug for, if you haven't tried AnyWidget in Python, you should. You can do a lot of really fun interactive data browsing here. So the last topic I want to briefly cover is electron tomography. So traditionally, as Pinchane mentioned, we do this kind of like a CAT scan or an MRI, right? You take a picture, rotate the sample a degree or two, take another picture, rotate, take more pictures, and then you use a computational method, a tomography algorithm in this case, to reconstruct the sample. But this is very time consuming. However, the results are worth it, in my opinion. This is a nanoparticle iron platinum hard drive sample. I drew two isosurfaces on the intensity field here, and you can see the blue is the higher level. Those are single platinum atoms, and the red is the lower level, the iron atoms. And so we are able to trace out every atomic coordinate here and solve the 3D structure and answer a lot of material science questions here. So the problem really is we can never tilt the sample 180 degrees. Because you have to hold the sample in the microscope, we're always going to have this missing wedge artifact, these missing projections. This is pretty bad in a continuous tomography sense. It's catastrophic for atomic resolution. There's a sort of threshold effect here where once you don't have enough tilts, you're no longer able to resolve atoms in 3D. And of course, if you undersample the number of projections, the same thing happens here. So these are just two quick toy models showing what happens if you do that. So our solution to this is, again, taken from the computational imaging literature, these NERFs, or implicit neural representations. So our first attempt at doing this used essentially MLPs, depth 4 network, I think, and we just treat it as a continuous reconstruction space. You query the network at x, y, and z coordinates, and you can do that along array, and that gives you the sort of pixel by pixel loss function that you can use to learn the continuous volume of the sample. And this is great for regularization too, because there are no pixels, there are no voxels, right? It's continuum, so you can compute things like TV exactly. And so if we apply that to a simulated phantom here, this is slicing through on the top row. The middle row is the implicit neural representation, and the bottom row is a conventional algorithm. You can see it's like night and day. Even if you have a tilt angle of only -40 to 40 degrees, you can still reconstruct most features of the phantom, whereas the conventional algorithm completely breaks down here. And if you undersample the number of slices, you get a very similar result, right? The INR is able to get a pretty good reconstruction with only 9 projections, whereas the conventional algorithm needs about 36 projections to be able to do a decent volume here. I should say it doesn't go on forever, though. For example, if you only have 5 tilts, the INR does produce a pretty nonsense reconstruction there, too. So if you're curious about our Tycho codes, we also have online, or Tomo codes, we also have online demos for them, too. OK, so last little bit here, the application to real-world materials. This is a TomVis render. Thank you, Kitware. On the left is the INR. The right is the conventional. The big improvement in quality here, you can see, is the lack of streaking. And this is because we're auto-differentiating the fine tilts and the fine shifts of the images, right? And this is done by a master's student who had never done an experiment before, which is very, very valuable to be able to get good reconstructions out of somewhat mediocre quality data. And so I'm just going to zoom in and show one slice here. Upper left, the INR reconstruction. Upper right, conventional algorithm. The conventional one is full of artifacts. Because of this large missing wedge here, you can kind of make out the catalytic particles, but these are catalytic nanoparticles sitting on a titanium oxide support, and the support is just as important for the morphology here of the catalyst. So the upper left also shows sort of 2 gray levels, and I asked the student what that was about, why the INR was making that prediction. We did a chemical measurement here and saw that it was actually amorphous carbon, which is lighter than TiO2. So simulations of this method on atomic resolution, it does amazingly here, right? You can do missing wedge inpainting very efficiently because atoms really are quite simple, right? They're round, perfectly round, isotropic objects, the first approximations here. We're also testing ways of speeding this up. The original INR architecture that we used took up to 16 GPUs, hours of reconstruction time. I'm a huge fan of the new papers on this K-plane factoring of TT, or tensor decomposition, because it runs much faster and produces even better results. So I'll end with one more example, combining ptychography and tomography. We did it in 2023 for this double-wall carbon nanotube with zirconium tellurium inside. And we were able to get every single atom, even the light carbon atoms, although it's a little sketchy in the missing wedge direction, and solve the structure here. So what we want to do next is do joint reconstructions of ptychography, tomography. And so here's my last slide showing sort of a work in progress. This is a really, really complicated, what we call polycrystalline sample of hafnium oxide. And we're trying to find every hafnium atom and every oxygen atom here. Unfortunately, this is unpublished because the project was interrupted because I quit Berkeley and moved to Stanford about 1.5 years ago here. OK, so if you want more information, all of our codes are public, many online tutorials, online data sets. And the 2 papers that I showed here, here's the archive publications for them. And so I definitely want to thank all the students and postdocs who did all of this work here, and you guys for your attention. Thank you.
Thank you. So now for questions. So we have limited time to take 1 or 2 questions over there.
Hi, a very nice talk. I think you mentioned that you have unlimited resolution, but and then my intuition is that if you want to have a better resolution, you need to increase the energy of the electrons, and would that not cause chemical damages?
The question is about the energy here. So actually, we've gone the opposite direction, right? What originally happened is higher energy, smaller wavelength of the electrons.
Yes.
So you went from 100,000 to 200,000 to 300,000 to 1,000,000 volt microscopes, but the damage just it explodes. So now most of our tools operate at 300,000 volts, but the highest resolution is when you drop it to 80,000 or 60,000 because you lower the damage, and then you use computational algorithms to make up the difference, essentially. So I actually think the future of transmission electron microscopy is more in the 20 to 60,000 volt range with computer algorithms.
So you mentioned about the sheer scale of data here. So right here.
Pardon me?
Yeah, hi. You mentioned about the sheer scale of data, like given the long capture time. So how useful have these deep priors been in compressing the raw data, given that there's so many redundancies in the pixel space, especially for like crystalline samples? So have they been useful?
Massively. I mean, machine learning is really all about compression, right? I don't think that's in doubt at this point. We are getting to the point where these algorithms are proving to be reliable enough that we're really hoping to be able to throw away the raw data. And so we actually have a project working with NVIDIA and the detector maker Dectris. We collect the data in about 3 seconds, transfer it to the GPU in ½ a second, run the reconstruction inline as data is streaming in, with the goal of deleting the raw frames as quickly as possible. And so if you can accomplish 10, 20, 30 loops of the training, and then clear out your RAM for GPU, now it's suddenly a time, you could do multiple time frames or collect tons more data here. The analogy, I think, is high energy physics here. If you look at the LHC and other giant tools like the Atlas detector, they throw away 99.99% of the data because they're really smart at triggering and only storing the important bits here. So yes, this is the higher dimensional the measurement, the more compressible the output. And I really do think machine learning is the key to using that fact.
OK, thank you so much. Due to the time limit, we can always continue discussion during the coffee break. Thank you so much.
Thank you.